The ends of this piece of metal are white hot. They're going to be joined together. Before the join can be made, the ends are bent round so that they overlap. Now the ends are still at white heat. In this state, they join simply by being hammered together. It takes quite a lot of hammering before the joint is completely made. We call this joining process forge welding. It's one of many different methods of joining materials. Here's another, a more familiar method known as gas welding. In this case, the joint is made by heating the materials to their melting point. The same thing happens in electric arc welding, the only difference being that the heat is obtained electrically. Here we're making a soldered joint. It's quite a different process, but heat is still involved. Sometimes heat is only used as an aid to a joining process, as in riveting. Can you think why the rivets are heated? And from riveting to bolting. These bolts are joining the framework of a crane together. Sheet metal can be joined by folding over the end of one piece and locating it with a similar fold in a second. For this method, we're using the metal itself to make the join, so it's often referred to as self-securing. And we can even use an adhesive to join materials together. In this car factory, an adhesive is being applied to the underside of the steel bonnet. This adhesive is being used to secure a steel stiffener which makes the bonnet rigid. In this program, we're going to concentrate on some of the processes where heat is involved. Let's start with gas welding. In this process, the heat is produced by burning a mixture of two gases, acetylene and oxygen. These gases are mixed together in a blowpipe which is held so that the flame is directed onto the area of the weld. Let's take a closer look. The temperature of the flame is just over 3,000 degrees centigrade. This is sufficient to melt the edges of the two pieces of metal being joined, in this case, low carbon steel. It's also sufficient to melt a filler wire or rod, which is often used in this process. Now, as the edges of the metal melt, they run into each other. We say they fuse together. This is what is known as fusion welding. This is what the surface of the finished weld looks like. See how regular and uniform the pattern is. Here's another process where heat is involved, manual metal arc welding. The heat is obtained from an electric arc which is established between a specially coated filler rod called an electrode and the workpiece. The temperature of the arc is between 4,000 and 5,000 degrees centigrade. The heat from the arc melts both the metal of the job and the end of the electrode. The metals fuse and the weld is formed. It's another example of fusion welding. During the course of this joining process, a coating of slag is formed over the surface of the weld. Normally, this slag has to be chipped away. Now we can see the surface of the finished weld. Let's take another look at manual metal arc welding. This time in slow motion. The action has been slowed down nearly 200 times. If you look at the workpiece itself, you can see it melting under the arc. It melts at the same time as the end of the electrode. You can also see the way the molten metal from the electrode behaves. As it melts, it forms into a blob. The blob grows until eventually it's drawn into the weld pool. Just after the metal of the electrode has melted, part of its coating evaporates. The remainder goes to form the slag on the surface of the weld. One great advantage of this process is that a great deal of heat is produced in a very small area. Another method of joining where the heat is supplied electrically. This time a current is passed through the join via a pair of copper electrodes. It's a form of resistance welding known as spot welding. Let's see the weld being made in cross-section. The action has been slowed down. The join is held between the electrodes under pressure. As the electric current passes through, it meets resistance and heat is produced. The heating effect is greatest at the center of the join. A combination of heat and pressure results in a nugget-shaped weld. Here, no filler material is used, unlike the normal fusion process. Welding as a joining process is not only confined to metals. Here we're welding a plastics material. Because this material melts at a much lower temperature, the heat source can be a jet of hot air. Do you think this is a fusion process? These pieces of copper are going to be joined by soldering them together. Soldering is a low-temperature method of joining materials. In this process, the components are heated not to their melting point, but to the melting point of a filler material or solder. The solder is an alloy of tin and lead. As the solder melts, it seems to be drawn into the very small gap between the two components. Let's look at a cross-section through part of the soldered joint. Here it's magnified nearly 300 times. The band in the middle is the solder, the top and bottom, the two pieces of copper being joined. Now, wherever the solder comes into contact with the two copper surfaces, a very thin layer of alloy is formed. It's an alloy of tin from the solder and the copper being joined. In order to produce this alloy and form an effective bond, the copper surface must be free of grease or any oxide layer. Here we're heating just an ordinary piece of copper sheet. As you see, the alloy isn't forming. The solder's running off. That's because there's a natural layer of oxide on the surface. Let's try another piece. This time we'll remove the oxide with wire wool. We'll also apply a chemical cleaner. We call this a flux, and this particular flux is a paste of zinc chloride. It's very corrosive, and could be harmful if it came in contact with the skin. The flux prevents any further oxidization on the surface. Let's try the solder again. That's better. This time the alloy forms. We say it wets or tins the surface. But how does solder get into a joint? Well, let's see what happens in the case of a simple lap joint. First, we'll heat up the metal. When the solder's applied, watch the edge of the join nearest to us. See how the solder has been drawn into the join. This is a natural process called capillary action. Let's see how all that occurs in practice. First, the joint areas must be prepared as before, mechanically, and then chemically, with care. Once prepared, the components can be fitted together. For the heat source, a mixture of natural gas and compressed air will do. Heat is applied uniformly all the way around the join. As the metal heats up, the flux prevents any oxide from forming. The solder, an alloy of tin and lead, melts somewhere between 180 and 320 degrees centigrade, depending on the proportions of lead to tin. As it melts, it's drawn into the joint, capillary action. Soldering is described as a non-fusion process. This is because it's carried out at a temperature below the melting point of the metals being joined. An alternative way of applying solder, particularly to light gauge components, is to use a heated soldering iron. This has a copper bit, which has been heated in a gas flame. Can you think why copper is used? In electronics, components are often soldered together. Here, the heat is supplied from a copper bit which is heated electrically. In this case, the flux used is one that is not corrosive. Why not corrosive? The flux is contained in 3 cores which run through the whole length of the solder. So far, we've looked at a non-fusion process called soft soldering. Another non-fusion process is hard soldering, sometimes called brazing. We're going to braze 2 bits of copper together. The joint preparation is much the same as before. However, the flux used is different. It contains borax. In this process, the flux is usually applied to both surfaces. In brazing, we also use a different filler material, one which has a higher melting point than soft solders. For a heat source, we're using a mixture of air and propane. Again, heat has to be applied generally to the whole joint area. As the joint heats up, the flux begins to act, just as it does when soft soldering. The filler material we're using in this instance is an alloy of copper, zinc and silver. See how it's drawn into the joint, capillary action again. Brazing has many applications in industry. For example, in the manufacture of electric motors. Here, the heat is supplied electrically using the heating effect of an electric current. The current is passed through the two parts to be joined. As the metals heat up, the filler or brazing material is applied. In order to keep the adjacent areas cool, a jet of water is used. Welding, soldering, brazing are all joining processes where heat is involved. Here's another, braze welding. That's the correct name for it, but it's sometimes known as bronze welding. It's another non-fusion process. The materials being joined do not melt. The temperature is only sufficient to melt the filler material, which is being deposited in the joint. It's not being drawn in by capillary action. This is what a braze welded joint looks like. We've used the process to join two copper pipes together. For this particular joint, one end of the pipe being joined is swaged out. That is, it's made into a bell shape. The other end can then sit inside. This type of joint is known as a bell joint. Both ends have previously been cleaned. For braze welding, we use a filler material which is an alloy of copper and zinc, sometimes with a trace of silicon. A flux is also required to prevent any oxide forming during the joining process. It's one that usually contains borax. The filler material has a melting point around 850 degrees centigrade. One way of obtaining this temperature is to use an oxyacetylene flame. The joint must first be preheated to raise it to a satisfactory braze welding temperature. This will be below the melting point of the copper, but above the melting point of the filler material. Once the temperature is reached, the filler rod is applied. It melts and flows over the surfaces of the joint. As it does so, the filler material intermingles with the copper surfaces and a thin layer of alloy is formed. This produces a strong bond. The rest of the filler material reinforces the joint. Can you think of any jobs where braze welding might be required?